Hello students. So in this session we will see the linear models of physiological systems. So we will take two examples of physiological system, and for that we will deduce the or estimate the linear models. The first example that we will take is the lung mechanics. So during the modeling of the lung mechanics, there are three things which we have to understand or we have to follow. The first thing, the pressure in the lung mechanics are considered as the potential or the voltage, and the airflow volume is considered as the current. So the airways are divided in human body. The airways are divided into two categories. One is the larger or the central airways, and second is the smaller or the peripheral airways. So these airways are presented with fluid mechanical resistances. So these resistances, like for larger or the central airways, we will consider this resistance as Rc, and the smaller or the peripheral airways, we consider that resistance as Rp. The air volume that enters in the alveoli also produces an expansion of the chest wall cavity by the same volume. So these are the resistances. So the expansion developed in the chest wall cavity and the alveoli are considered as the lung compliance and chest compliance. So the lung compliance is considered as the CL and the chest compliance is considered as the CW, and it is represented as the capacitor in the circuit. Further, a small fraction of volume of air that enters the respiratory system is shunted away from the alveoli because of the compliance of the central airways and the gas compressibility. So that is represented as the CS. Further, this shunted volume is very small under normal circumstances. So in normal breathing or normal breathing rate, this is very small, but it becomes more and more substantial if there is any disease to peripheral airways, um, or if there is any obstruction. So if this Rp increases or the stiffness of the lungs or chest wall increases, there will be a decrement of lung compliance or this chest compliance. So that's why it is connected as a shunt element in the circuit. Now this effect is incorporated by placing a shunt compliance in parallel to the CL and CW. Further, the pressure developed at the different points of this lung model are: at the airways opening, it is PAO; at the central airways, it is PAW; in the alveoli, it is PA. The pressure between the lung and chest wall, it is PPL, and here the reference voltage is taken as the PW, that is also the ambient pressure, and maybe for the analysis we can set it as 0, like in the circuit we normally ground, so this can be considered as a ground. So this is the inhale volume rate, that is represented as Q. So the objective here to derive a mathematical relation between the PAO and Q, the inhale volume rate. So the volume flow rate in the alveoli is represented by QA. So if we apply the KCL at this particular point at X, we can say that the total current is Q. If some part of current is there, this QA, then the rest of the current, that is the Q minus QA, will be on this side. Then if we apply the KVL in the loop 1, this equation can be generated. So this is QA into RP with potential drop with the minus sign. Then the potential drop across this capacitor will be minus 1 by CL, integration of current passing through this particular capacitor, that is QA. Then one term is missing, so we can add that particular one term with the minus 1 upon CW integration of QA dt. So this will also be there, and then because of this capacitor, this particular potential drop will be there, that is with the plus sign 1 by CS integration of current passing through this particular capacitor, that is Q minus QA into dt. So if we apply the KVL in this particular loop, we will get this equation. So the potential drop PA0 minus Q into RC, then again the potential drop across this capacitor across CS, that will be 1 by CS integration of Q minus QA into dt is equal to 0. So this is considered as a ground. So now we differentiate both of these equations and we will get this and this equation. So these are just the differentiation of the given or derived equations. And from this equation we can get the value of QA, and to get the value of differentiation of this QA, we again differentiate this particular equation and we will get the value of differentiation of that QA. So now we will replace the value of QA and the differentiation of QA from these two equations. So these value will be replaced and we will get this particular equation. And finally, if we solve this particular equation, this will be the final equation that represents the human lung mechanics. So this is a second order equation which relates the input pressure and the input, we can say the airflow volume in the lungs. So now the second example is like we will develop the linear model for skeletal muscle. So it's the skeletal muscle. So skeletal muscles are basically attached to the bone with the tendon, or we can say the skeletal muscles are attached to the bone by tendons, and they produces all the movements of body parts in relation to each other. So the force developed by active contrail elements, we can consider that force as F0, this particular force. Then the actual force after considering mechanical properties of the particular muscle, that is this force F. And the viscous damping of muscle is represented as a damper with the damping coefficient R. The storage property of elastic sarcoma is considered as the Cp. So in mechanical domain, the energy storing element is considered is represented as the spring. So these elements, this particular element and this particular element is depicting the spring, and these are not the spring coefficient. That Cp is not the spring coefficient. This is the inverse of the spring coefficient, that is known as the compliance. Similarly, the storage property of muscle tendon is represented as Cs. So now the mechanical constraints placed on the model components. So let's see, if spring Cp, this particular spring, is stretched by an incremental length x, the entire series combination of R and Cs will also extended by the same length, that is x. The sum of force transmitted through the two branches of parallel combination, these must be F. Although the sum of extension of Cs and R will have to equal by x, but the individual length contribution from Cs and R, these are not needs to be equal. This can be different. So here we have taken this x1, and for this R we have taken the extension contribution as x1 minus x. Next, if we sum Cs, if we assume that Cs is stretched a length x1, then the extension in the parallel combination of R and F naught will be x minus x1. So as we stated earlier, that the C, which is represented as Cs and Cp, these are not spring coefficient or spring constant. These are the compliances of the spring. So it is the inverse of the spring constant. Okay. So now the velocity with which the dashboard or the damper is extended, that will be d by dt of x minus x1. And if we balance the force at this particular point, we will get the force balance equation, that is the x1 by Cs is equal to force F naught plus R, the moment balance, the R, and the velocity of this particular damper, and that is the d by dt of x minus x1. And also if we see the total force in both the limbs or both the branches, we can get like the total force F is equal to x1 upon Cs plus x upon Cp. Now here we see that under steady state isometric condition, the muscle length is considered as a constant. So the force developed by the muscle model will reflect the force developed by the active contrail elements of the muscle. So if we equate the previous equation, we will get that F, these are the previous equation that we have derived. So if we replace the value of x1 from both the equation, we will get this. And as per the statement, under steady state isometric conditions, that means the muscle length is considered to be constant. That means the x will be 0, the rate of change of x will be 0, and the rate of change of force will also be 0. So that particular equation comes out as F is equal to F naught. So like this, we have developed the linear model of physiological system for skeletal muscle and also for our lung mechanics.